You're listening to the Thesis Review podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. My guest today is Yoon Kim, who is currently a research scientist at the MIT-IBM AI Watson Lab, and will be joining MIT as an assistant professor in 2021. Yoon's research focuses on machine learning and natural language processing, and his PhD thesis is titled Deep Latent Variable Models of Natural Language, which he completed in 2020 at Harvard University. On today's episode, we discuss his work on uncovering latent structure in natural language, including continuous vector representations, tree structures, and grammars. We cover interesting learning and variational inference methods that he developed during his PhD, and he offers a look at where latent variable models will be heading in the future. The Thesis Review is available on SoundCloud, Apple Podcasts, Google Podcasts, and Spotify. And be sure to follow on Twitter at Thesis Review. If you would like to support the podcast, you can buy me a coffee at buymeacoffee.com/thesisreview and contribute $1 towards coffee funds. There are links to Yoon's thesis and the papers that we mentioned in the show notes. Here's Yoon Kim with Deep Latent Variable Models of Natural Language on the Thesis Review. So your thesis involves automatically discovering or finding structure in language.
Mhm.
So do you think that language has some true underlying structure? And if we did discover, or how would we know that we discovered the true structure versus just some other structure?
I am a very naive linguist and a cognitive scientist, so whatever I say is going to be probably very wrong. But my view on this, and it's an interesting, almost philosophical question because it does inform how you approach, how you model language. My view is that these types of structures, like grammars, that are purported to govern human language acquisition, are nice enough mathematical abstractions that are computationally tractable to work with. So any learning that happens through these structures, I think, nice approximations, interpretable somewhat approximations to real world phenomena, which is language. Whether these structures are real, i.e., is our brain implementing a grammar? I don't think so, but again, I don't know enough about psycholinguistics, cognitive science to comment more intelligibly. On the one hand, I think the world would be too nice if that were the case, and the world is messy. So I don't know. But on the other hand, like one of my favorite quotes is from Jason Eisner. I may be misremembering, but it says something like, either the world is hierarchical or there is a god, or it could be either the world is compositional or there is a god. So the fact that like hierarchical structure, compositional structures are ubiquitous in sort of any physical phenomena could be a case that these types of structures that we posit to govern language are, in some sense, physically grounded. But again, I don't know enough about these areas to comment more intelligibly. But my take on it is these are just good tools we have to model natural language data.
So yeah, you could kind of approach it from a psycholinguistics perspective or linguistics perspective and maybe argue for some structure.
Right. What's interesting though is these types of hierarchical structures, there does seem to be enough neurobiological evidence that for example, something like parsing is happening in the human brain, and of course, the exact mechanisms by which these structures are built are under much scientific debate and investigation currently. But it seems like there's quite robust evidence that something like parsing is happening.
Yeah, so certainly even if we might not get some kind of exact true structure, there is some sense of structure, it seems like. And I guess what
Right,
you're saying is that
right.
there's something that can help computationally to model language.
Yeah.
Your thesis, it's titled Deep Latent Variable Models of Natural Language. Um, so maybe first, could you just define what latent variable models are and how you got interested in these?
Sure. So latent variable models are essentially, in my view, joint distributions over observed variables, typically x, and unobserved latent variables, typically z. And then we
Hmm.
have some parameters for this joint distribution, say theta. And of course, latent variable models have been one of the classical machine learning tools for discovering structure in natural language data or for things like structure prediction. An advantage of latent variable models is that um, the joint distribution or the factorization of the joint distribution into conditional distributions gives the modeler a powerful tool to imbue your generative model, your joint distribution, with the right inductive biases. For example, in a
Mm.
HMM, there are conditional independence assumptions in the HMM that lead to, for example, part of speech like uh, tags that become discovered once you uh, learn this generative model, latent variable model. So that's a latent variable model. What I mean by deep latent variable models is that we still use the language, the declarative language of latent variable models to um, factorize the joint distribution into conditional distributions. And this is, again, specify the modeler and is dependent upon what kind of language phenomena or any underlying phenomena that you want to model. But in deep latent variable models, we parameterize these conditional distributions with neural networks.
Hmm.
And there are two reasons why you might want to do this. One is that neural networks allows you to flexibly parameterize your conditional distribution over high dimensional combinatorial input without an explosion in number of parameters. For example, if you
Mm.
consider, say, a naive Bayes model, which is classical, the reason why typically the naive Bayes assumption is made is because otherwise conditioning on the latent variable z and the past history would quickly result in a blow up in terms of the number of probabilities that you need to estimate. But if you condition
Hmm.
on the history with, say, some sequential neural network like an RNN or a transformer, then you can compactly represent a combinatorial distribution. You can compactly represent a distribution of the output conditioned on a combinatorial input with this neural net. So that's one advantage of having these deep latent variable models, i.e., neural parameterizations of conditional likelihoods. Another reason is that even if you have the same conditional independence assumptions, turns out there's something almost magical that happens if you parameterize these conditional distributions over, say, neural nets over embedding representations. And I'm not exactly sure why this happens. And the analog is something like a non-latent variable, say, feed-forward language models. You can have, say, a feed-forward 3-gram language model where the distribution of the output is given by, some concatenation of the history, where you feed that through a neural net. Typically, that
Hmm.
does better than just a regular count-based language model where you actually do the exact maximum likelihood estimation by counting and dividing. Um,
Mm.
and so if you don't smooth, then like this typically sort of Bengio style feed-forward language models do well, which is strange, right? Because on the
Hmm.
one hand, you have counting and dividing, which is your exact MLE solution, whereas on the other hand, you have some neural net solution. I think there's some similar effect like that happening here, where through parameter sharing over these embeddings, there's more
Hmm.
statistical efficiency. Um, yeah, so one phenomena that I found is that even if you have the same exact probabilistic model in terms of the factorization of the conditional distributions, typically if you parameterize these modular components with neural nets, that does better both in terms of structured discovery and training objective. but I don't know why that happens, and I wish someone like smarter than me would figure this out.
Yeah, that is really interesting. So you're saying it's kind of analogous to one of these n-gram language models, and just by using the neural parameterization,
Yeah,
something is happening there, which helps it to generalize better.
right.
Well, luckily we have plenty of smart people, I'm sure, listening to this podcast, so hopefully someone will figure it out now. Going into your PhD, did you know that you wanted to focus on these types of latent variable models or deep latent variable models, or at what stage did you kind of pick up an interest in this area?
Oh, yeah, most definitely not. I couldn't have imagined, for example, going in that I would be spending a couple of years doing like grammar induction.
Mm,
Actually, going into my PhD, I was like a very much deep learning purist, where
mhm,
let's get some data, put it through a neural net, predict something, get a number, and optimize that. And essentially, I think the first couple of works during my PhD were in this, vein of purely deep learning empirical work, mostly in the realm of supervised learning.
mhm,
And then I sort of got interested in latent variable models through like the VAE literature, and I spent a year trying to make VAEs work for a language, like sort of sentence level modeling, and it's not clear they still work as well, but that was my foray into latent variable modeling from the perspective of like sort of deep generative models, i.e., deep where your joint generative model is given by a neural net, and you do inference over this. You do approximate inference over this typically intractable model with another neural network, i.e., the
mhm.
inference network. So that's how I got interested in latent variable models, um, and then at the same time, I was just taking a couple of linguistics classes, and this notion of like grammars and syntax. Again, I don't know enough to. I'm probably like I don't know enough to comment intelligibly, but it seemed like there was something there. Um,
Mhm.
and then I think that's how I got interested in grammar induction. And then trying to discover these hierarchical structures from data. Yeah, certainly. To go back to your original question, is something I never planned. I think during my PhD, I just kind of did what seemed interesting. Like my personality type is that if I have an interesting idea that I think is interesting, which typically turns out not to be interesting afterwards, but I like have to try it. So like
Yeah, yeah.
yeah. So I don't think there was any like plan on doing this type of work through my PhD. Certainly not.
You were kind of driven to investigate these models out of interest versus saying, like, I want to, I don't know, achieve better performance on a specific task or something like that.
Yeah, and especially with grammar induction, because I think especially nowadays, it's like classical. One of the classical motivations for grammar induction, one of the classical motivations was, oh, like there are many domains and languages in which having access to these types of induced trees would be useful for some downstream engineering task, and that may still be
Mhm,
true for some like low resource languages or domains, but
mhm,
uh, in the current paradigm of these giant pre-trained models on self-supervised objectives, you think the engineering case for grammar induction is becoming smaller and smaller. But I think it's still a very interesting question from a scientific standpoint, in that,
mhm,
for example, the amount of inductive bias that you instill into your artificial learner, and whether your learner is successful at discovering the syntax of language um, just from raw text, I think tells us something deep about the classical debate between the nativist and the learning based theories of human language acquisition.
There does seem to be something nice about working with these models and these latent variables. There's almost something mysterious, like what sort of structure will they
Yeah,
find?
and it's very frustrating as well. Like not only does the conditional independent assumptions that you imbue into generative model matter, but how you parameterize these like individual conditional distributions also matters. So there's like
Mhm.
inductive bias from the factorization of the generative model itself, and there's also like inductive bias in how you use a neural net to parameterize each of these smaller components. So it can be a frustrating exercise as well, trying to get these
Mhm.
models to discover the right structure.
So yeah, hopefully over the course of this conversation, we'll go into a few
Mhm,
examples of this. You focus on this, like it's focused around this variational inference
mhm.
approach. Do you maybe want to just introduce that at a high level?
So one way to learn these generative models, again, which are just joint distributions over p, z, and x, is through maximum likelihood learning. And depending on how you factorize this joint distribution, you can marginalize out the z. So you get p of x, the likelihood, um, through sort of some tractable summation algorithm, whether it be dynamic programming and sort of classical factored models or just enumeration. And
Mhm.
in that case, you can maximize this log likelihood p of x through whatever method, whether it be EM or gradient ascent. Now
Mhm.
there are cases in which your and then going actually into the EM approach. One critical part of this EM approach is doing posterior inference over the latent variable z, conditioned on the data x. So you need this object pz given x. And
Mhm.
again, in classical models like HMMs, this is tractable to estimate. So exact posterior inference in many of these classical models is tractable. But
Mhm.
once you get into sort of neural parameterizations, then there are many cases in which this posterior inference, i.e. pz given x, becomes intractable.
Mhm.
And a classical approach to getting around this is through variational inference, where you posit this variational family of distributions which are going to be learned, um, and this will approximate the true posterior distribution. And one can show that the log marginal likelihood, i.e. log p of x, is lower bounded by this quantity called the evidence lower bound, which makes use of this variational distribution. And the
Mhm.
classical approach to learning intractable models with this variational approach was to do an EM-like approach, where in the E step, you perform variational inference for each of your data points. So you approximate the true posterior distribution, and then in the M step, you maximize the log joint likelihood px given z under the expectation of this approximate posterior distribution. So that's
Mhm.
sort of classical variational inference, and this leads to methods like coordinate ascent variational inference in conditionally conjugate models, and stochastic variational inference, where you can do gradient ascent to do variational inference. A drawback of these types of approaches is that typically you still need to do inference for each data point separately, and this could be expensive uh, if you have, say, millions of images over which you want to do inference. And this is where this technique called amortized variational inference comes in. And this was introduced in 2014 from a bunch of groups, Kingma and Welling, Razende and Muhammad, and Andre Ni, and some other folks at DeepMind as well. And
Mhm.
and this has roots going back to some work in 2000s as well, where I think actually your advisor might have some work where he used similar ideas to initialize the starting distributions of restricted Boltzmann machines with like these types of learned inference networks.
We'll have to see if he's listening. If he's listening, then he'll.
uh, yeah. Now you have this in this amortized variation inference. Instead of doing per data inference, you predict the parameters of your approximate variational distribution to be feed-forward function of your input, which is parameterized as a neural net. And this is
Hmm.
really cool because it transforms the task of inference into prediction. Actually, to go uh, to go back a step, variational inference is itself cool because it transformed the task of posterior inference into optimization over this variational family, and then amortized variational inference transforms this optimization task into a prediction task. Um,
Hmm.
and an advantage of this is that you can now do sort of easier inference, approximate inference of your data point by just passing um, this inference network of your inputs and then obtaining the variational parameters. And
Hmm.
then you can train both the generative model and this inference network end to end on this quantity called the evidence lower bound.
Yeah, so it's like a nice neural version of variational inference in some sense.
Right. And that's sort of like the core technique in my thesis, where I'll be typically working with deep latent variable models, which for which exact posterior inference is intractable. So we want to do approximate inference over them, and then to do this, I'll employ another neural network, this inference network, to obtain the parameters of the approximate variational distribution. And a lot of my thesis considers sort of different takes on how to adapt this broad technique of amortized inference for different applications of interest.
Yeah, and that's a great lead in. So one thing I really liked was you had this table at the end of the background section,
Mhm.
and it kind of breaks down the rest of the thesis in terms of what type of latent variable you're dealing
Right.
with, and the type of generative model, and
Mhm.
then the type of learning and inference procedure that you developed.
Mhm.
We could start with the first one, which is a continuous latent variable.
Yep.
And here you're dealing with modeling sentences or text.
Right.
What would be the hope for a latent variable model of sentences?
Yeah. So the ideal hope with that type of model. So just to give the readers background, this is a classical sentence VAE originally proposed by Sam Bowman, who's of course at
Mhm.
NYU too, where we posit a latent variable which ideally governs sort of the long range um, dependencies in a sentence or the topical elements of a sentence, and that is coupled with a neural network decoder. Actually, I don't like to use the word decoder, a neural network generative model that
Mhm.
conditions on the latent vector Z and the history through some autoregressive methodology, autoregressive factorization. And Sam Bauman had this very nice paper in 2015, and
Mhm.
it turns out the result was somewhat negative in that
Mhm.
if you had a lot of optimization tricks, like penalizing certain parts of the objective, you could get it to work, but a lot of the time, the generative model just learned to ignore the latent variable.
Mhm.
And I think after wrestling with this, the community realized, oh, this sort of makes sense from an optimization standpoint. If you have a flexible enough generative model, i.e., say a fully auto-regressive RNN, then if the model can use that to model the underlying data, P of X, without using the latent variable, then
Mhm.
it doesn't have to pay the penalty for this portion of the elbow, which is the KL divergence between QZ, given the variational distribution and the prion.
Mhm.
And I think the interesting question at the time this work was going on was like whether that was the full story, i.e., is it just due to this sort of the expressivity of the generative model? And of course, this had led to a lot of other interesting work on making the generative model less flexible, like making it convolutional or even just a backwards model.
Mhm.
And this work, initial work, was looking at now asking the question whether this was again just due to the expressivity of the generative model, or is there something that happens because we're doing this thing called amortized inference. And what we found was like this idea of amortized inference, where you transform the problem of optimization into a neural network prediction problem, is a powerful technique for doing efficient approximate inference. But the family of variational distributions that you get through this is a subset of the variational distribution that you get from, say, a classical variational inference method, because you're not able to do sort of like per datum inference.
I see.
Yeah, so in this work, we looked at whether improving this amortized inference method by uh, augmenting this amortized inference with more classical per datum inference techniques uh, would
Mhm.
enable learning of generative models that don't ignore the latent code, but allows you to have a very expressive generative model. And the result was somewhat like yeah, there wasn't total ignoring of the latent variable, but the method was quite slow. So it's not clear it's going to be like useful. But that was the context of the this work that you mentioned, which was the first I guess chapter of my thesis.
So yeah, that was this semi-amortized
Right.
variational inference was the name for it. Maybe the initial work on this was kind of mixed because of this posterior collapse issue.
Mhm.
But in general, like looking back or looking forward, do you think that trying to incorporate these continuous latent variable models for text generation has either certain applications or can help with getting lower perplexity or something like that?
No, my answer to that is pretty much no.
Okay.
And yeah, so I've changed my thinking around like these types of latent variable models that fully condition on its history, and
Uh-huh.
um, I see no like good reason to use them. Um,
Mm.
so and like again, maybe I'll change my thinking on this over
Mhm.
the next year or two. But like, why do we want latent variable models? One reason is we want to discover structure from data. So from that
Mhm.
perspective, like we want our latent variable models to then have some conditional independence conditioned on the latent vector z, so that
Mm.
if you think about the infinite data, infinite model capacity regime, the latent variable will still learn something, right? And it's not clear that's happening in these models where it's fully conditioning on the past history, i.e., the model is basically not identifiable. So that is a case against these types of models from the perspective of learning structure. Even from the perspective of generation, it's not clear like that these latent variables will encode what you want it to encode through just simple
Mhm.
training, right? Um, and like after training, we do find that these latent variable models do encode more. They're more sensitive to parts of the sentence that encode things like lexical nouns and verbs. But just relying on just doing, hoping for that to emerge um, seems like too futile of an exercise. So I
Mm.
think
I
these
see.
types of like straight up fully autoregressive generative models that have a latent vector at each time step may not have much utility. But where I do see interesting stuff happening is now where you're able to provide some sort of like supervision on this latent vector through some means, right? One example of work
Mm.
which I really love is the controllable text generation work from Jiting, where he provides some supervision into the latent vectors that he's learning. So this framework, insofar as these models can be combined with other data sources or other ideas that allow you to inject what you want to learn into the latent vector, that facilitates some level of controllability and interpretability in the generation process. I think these are useful, but on their own, I think, like for example, I don't think that we should be training these models to get lower perplexity, even though that's
Mhm.
exactly what I did.
Yeah, I mean, that's a valuable perspective though, to kind of like reflect back. And so, yeah, so I guess what you're saying is in terms of language modeling, if you have an autoregressive language model,
Mhm.
then it's probably powerful enough on its own. And then if we want something like interpretability,
Mhm.
it's probably most useful to declare what type of interpretability we want through
Right.
some labeled examples.
Right. And then actually, like, one person who made me change my thinking on this was again your advisor, where like, we're talking, and he I may be I'm surely like misremembering the exact wording, but it was something like, given a no, given a model that does experience posterior collapse and therefore just becomes a language model, is there
Mhm.
a model that has the same type of conditional inference assumptions that doesn't experience posterior collapse, but when you marginalize the latent variable out, you get the same perplexity. And initially, like, I didn't even understand this question, but like after thinking about it, like, yeah, there has to be, like, because when you marginalize these models out, they just become models over P of X, right? So
Right.
just from the perspective of getting lower perplexity, I'm not sure there's a strong case for these latent variable models in rich data and rich model regimes.
So if the autoregressive nature, so if the fact that the generative model or the decoder is too powerful
Mhm.
is an issue, do you think that these could potentially be promising for, say, non-autoregressive generation, where you could have a latent variable to capture the global structure, and then
Mhm.
your decoder has these conditional independence assumptions?
Yeah, totally. And there's a really nice, rich line of work on these types of latent variable based non-autoregressive generation, and I think that that's such a nice application of like a pretty cool technique. And these are combined with things like flows, where yeah, that's a cool application of latent variable models uh, for practical benefits in contemporary deep learning based NLP.
Okay, good. So there's still hope.
Let's hope so. Yeah.
We could, I mean, we could return to the attention if
Mhm.
there's time, but I want to make sure we talked about the latent variable being an unlabeled binary parse tree,
Yeah. Sure.
because this was really interesting to me. So now instead of a continuous vector,
Mhm.
not only is the latent variable discrete, but it's also structured. So
Mhm.
structured according to a
Yeah.
tree structure. And then the generative model is this recurrent neural network grammar.
Yeah.
So, yeah, did you maybe want to talk about just how this investigation got motivated?
Yeah, sure. So maybe we can start with a little background on recurrent neural network
Yeah.
grammars, which was introduced by Chris Dyer and colleagues in 2016. And these recurrent neural network grammars, RNNGs, are basically generative models of sentences and trees. So these are joint generative models, say PZ and X, where X is a sentence and Z is your tree. And what makes these different from classical, say, RNN language models is that the generation is a hierarchical process as opposed to a flat left to right generation process. In that, as you generate a sentence, you maintain a stack, and
Mhm.
as you generate a sentence, you complete constituents as you generate these sentences and update the stack with representations of these completed hierarchical structures, which are constituents.
Mhm.
And what's really fascinating about these models is that um, they really exhibit. So actually, just from a language, just from a pure machine learning standpoint, they're very interesting because they typically outperform regular language models when you train on the same amount of data. So it's interesting from that point of view as well. But from a
Mhm.
scientific standpoint, these models are very interesting because they truly exhibit different uh, they learn to generalize syntactically in a different way than your regular language models. And this has been borne out through a bunch of experiments. Roger Levy and colleagues at MIT have a bunch of works that test these models vis-a-vis the flat RNN language models on psycholinguistic stimuli. Um,
Mhm.
Chris Dyer, John Hale, Jonathan Brennan, and colleagues also have some work where they correlate certain metrics derived from this model against electrophysiological activity in the brain and show that it correlates better or even on top of these flat left to right language models. Actually, which is one sort of evidence for reification of these parse trees in the human brain. But let's close that
Hmm.
parenthesis. So these models are just fascinating, both from a machine learning standpoint and from a cognitive science standpoint. And in fact, I think there's a rich research program around RNNGs in the cognitive sciences, trying to compare them against human language processing. But in the original work, this model was trained on a supervised tree bank, i.e., the Penn tree bank. And of course, one thing that motivated the unsupervised RNNG work is that when children acquire the syntax of their native language, they don't do it with the textbook-like supervision that we give to our supervised learning algorithms, right? No one tells a baby here's a English sentence, here's a parse tree, learn a mapping. Um,
Hmm.
Again, there is some debate as to how much implicit supervision that children get when learning the syntax of their native language, but clearly it's not, like the textbook like supervision. So an
Hmm.
interesting question then is like, um, can we, use these RNNGs, but somehow discover the underlying structure without supervision? So that was the main challenge of the work. And the way we tackled it was again through this overarching technique of variational inference, where we now parameterize a distribution over binary trees, which are going to be parse trees of a sentence. With some neural net, we used a neural conditional random field, and as soon as you have this automatically gives you all the machinery of variational inference, and you can crank this machinery and essentially train the model. What was a challenge in this model was that because the generative model is too flexible, and this actually mirrors the discussion that we had with regard to having too flexible of parameterizations in generative models, hindering the learning of interesting structure in the continuous
Right, right.
PAD case. But the RNNG is also the latent variable is discrete, but it's also a very flexible model in that it fully conditions on the previous history. So
Hmm.
the challenge was, how do we somehow encourage the model so that it learns meaningful tree structures? And what we found to be effective enough was imbuing using a more constrained variational inference network, variational posterior distribution, which is a CRF parse, constituency parser. And we found that to be crucial in learning somewhat meaningful tree structures from raw text while maintaining the good perplexity characteristics of the original RNNG. But actually, again, like looking back on this work, I do think still like uh, I think it was a happy accident that we found a parameterization of the variational distribution and uh, the neural network that parameterized the variational parameters of that distribution, right? And
Hmm.
and I just got lucky and stumbled upon this parameterization, which made use of other work as well. But I do think this is like maybe not the correct approach if you're interested in learning good structures.
Yeah. So there's a few things that that was like a really good overview. There's a few things that I would want to expand further. So like
Mhm,
first, so you mentioned this correspondence that has been investigated between the recurrent neural network grammar and what might happen in the brain.
mhm.
So maybe that's one argument for using this constituency tree form. I was just wondering, like, why did you choose to use constituency trees versus, say, dependency trees? Maybe it has to do with the grammar induction task. I think maybe people focus on constituency parsing more.
It's funny actually. Moose grammar induction worked on not maybe overgeneralizing, more like dependency based structures, because
I see.
Getting constituency structures, and this was the classical, based on the classical DMV work from Dan Klein and Chris Manning.
Right, right.
Um, and I talked to a couple of researchers regarding like, oh, why the focus on dependency grammars, and the answer was like because the constituency induction problem turned out to be much more difficult, not mathematically but
Mm,
just empirically. But I think there may be, again, I don't know enough linguistics. There may be well motivated reasons to use one structure versus the other, but to me, I just did constituency structure because that's what the original RNG work did.
uh-huh. Yeah, that makes sense. So you kind of alluded to this that in practice it was maybe difficult to get these to train.
Yes, and this was an example in which it was not just enough to use a CRF inference network, right? That's the class of variational distributions. But it was
Mhm.
important to use a certain parameterization of the neural net that gave the logits or the parameters of this variational inference network.
Yeah, so then I'm guessing like in initial experiments, you were just getting like all left to right trees or all right to left trees or something like that.
So initially, when I was working with a non-CRF inference network, so a transition-based parser that just looks at the entire sentence, I wasn't able to get anything. And then when I moved on to the CRF inference network, like it sort of worked out of the box, and I got really lucky because I was thinking about how to parameterize the logits of your CRF, and I just took a standard parameterization that I think Mitchell and Stern proposed from Berkeley for training constituency parsers. And I just randomly happened to have read that recently, and I was like, oh, this seems to work nicely. So I just did that, and it worked. But had that not worked, I think, and then when I actually look back and I used like a different parameterization, it didn't work. So
Mm,
had that first parameterization not worked, I think maybe I would have given up.
yeah, interesting. Recently, there's been this PyTorch struct library that was
Mhm.
developed,
Yep.
probably motivated by some of these issues that we're talking about in your work.
I think part of this was motivated by my advisor Sasha looking at my horrendous code and seeing, oh, like we can like make this much much faster and more efficient. And I'm actually using that library for my current project, and like, oh man, like yeah, it's I thought my optimization was like decent, but damn, like yeah, this library is on another level.
So you said with the messy code, but like a more generous perspective is that you like went really deep into this problem, and then we probably didn't even realize that these are good things to provide in
Right,
a library
right.
potentially. And so I just want to ask, like, if you redid this project now using that library, would it have any difference, or do you think that there's still issues, I guess, with this parameterization that um, it still would be difficult to get it to work?
Yeah, certainly it'd be a lot less lines of code, but I think the whatever feeds into this PyTorch library, which is just CRFs. Um,
Right.
but yeah, maybe iterating through that experiment, the different parameterizations might have been easy if I didn't have to worry about getting the entropy and samples and all that.
Yeah. Yeah, I see. So the next section's on these grammar and continuous vector
Mhm.
latent variables. And the generative model is called compound probabilistic context-free
Yeah,
grammars
yeah, which I regret now naming, but
because it's too long of a name, or
oh no, because like it's not actually it's not like a PCF. It's not a context-free grammar in the classical sense, at least.
oh,
Um,
I see.
yeah.
So to me, these seem somewhat related. What was this kind of a next step to the unsupervised RNG, or
Um, so I didn't think about the connection between the two, but I think one way to make a connection is like with this UR with the unsupervised RNG work, you're starting with a very flexible generative model that doesn't really have inductive bias to discover these tree structures, and then you're saying, oh, how can we somewhat guide the learning process such that it discovers meaningful tree structures, and we do that with a variational posterior distribution that is more restrained. So it's like an example of a classical posterior regularization framework. So, i.e., you
Hmm.
start with a very flexible model and then you regularize its posterior. And I think maybe one way to characterize, one way to contrast this compound PCFG work is starting from the other end. I.e., can we start with a pretty classical but a weak model that does have strong inductive bias, i.e., a
Hmm.
PCFG, and can we make that more flexible with like deep learning? Yeah, I think that could be an interesting way of contrasting these two works, but putting them in the same family of these lines of work that want to discover meaningful structure from text, but also ideally model the underlying data well.
So then, in this case, again, the structure that it's attempting to discover is the constituency tree, right?
So in like empirical practice, there's no distinction between like trees and grammars because these are evaluated as unsupervised parsers. But I do think there is a deep distinction between discovering trees and discovering like grammars. You can do unsupervised parsing without inducing a grammar, but if you induce a grammar, that gives you tree structures for free.
Yeah, yeah, that makes sense.
Mhm.
So then, what was the kind of key idea behind this work?
Yeah, so there were two key ideas. One was sort of revisiting the classical PCFG, which yeah is sort of one natural model of human language. I think there's still debates as to whether human languages. Oh, certainly, like it's been proved that certain languages are not provably not context free. But I think there's some debate as to still like whether English is context free. But anyway,
Mm.
that's a side note. But these do seem like sort of nice enough formalisms that have tractable algorithms for inference. Um, to discover grammars from text again, which and once you discover this context grammar for text, they give you parse trees for free. um,
Hmm.
but it turned out for the past 20, 30 years, like inducing these grammars from text with these PCFGs was very hard. There had been some successes on like very short sentences with gold pot of speech tags, and also if you have some sort of like bounds on how deep you want your trees to be. But this was like an empirical puzzle where we had this very almost very beautiful model of language that should work if you do maximum likelihood learning, but just didn't. The trees you
Hmm.
got didn't really correspond to linguistically annotated trees. So the first contribution of this work was like revisiting this classical grammar, and again, like thinking about how do we neuralize this distribution, where we have the same conditional independence assumptions, the same generative model, the same PCFG, but we parameterize the distributions to be outputs of neural nets. And
Hmm.
it turned out the simple change allowed us to train somewhat linguistically meaningful grammars through simple maximum likelihood learning, which was like I think pretty cool result. And I think it's probably like um, the more surprising aspect of that work than the second extension, which I'll talk about. So this was again a classical PCFG, but with a neural take on it. In the compound PCFG, which is sort of our second addition to this, um, we try to model long-range dependencies within a sentence with a sentence level latent vector. And the reason we might want to do this is that even if, say, English were context-free, um,
Hmm.
the classical PCFGs that we're working with are not large enough or flexible enough to model like the richness of English language. For example, it's clearly not. So there's. It's not a. We weren't working with, for example, a lexicalized PCFG. And in principle, we could work with them, but this quickly results in an explosion in the number of rules in your context-free grammar. So even if exact posterior inference were tractable, it becomes intractable in practice to train these models. And in this second extension that we call the compound PCFG, because this is an example of a compound generative process, we almost as a hack approximate these richer dependencies in a sentence with a sentence of a latent vector. And
Mm.
sort of like a TLDR of this work is it's like a VAE with a PCFG decoder. And we found that this resulted both in better structure learning and a better model of language as measured by perplexity.
And then you also evaluate on the parsing capability.
That's right. Right. So we evaluated the grammars as an unsupervised parsing system, and we found that they were able to do well, which was exciting. So one of the classical uh, negative results in NLP and grammar induction was that if you train these PCFGs on like the full PTB, you get a
Mhm.
grammar out, but the parse trees that you get underperform trivial tree baselines, like right branching baselines in English, which is pretty good because English is a head initial language. But it turned out with this neuralization, this neural PCFG, we were able to train PCFGs that outperform the right branching baseline. And with the compound PCFG, which enriches the PCFG with long range dependencies with the sentence of a latent vector, we outperform this neural PCFG as well.
So then here there's some form of label that you have to decide,
Right.
right, in this grammar.
Mhm.
So how do you, if you just have discrete latent variables, how do you decide which discrete element corresponds to which semantic label
Yeah, that's a great
when you're going
question.
to evaluate?
In the current setup, the convention is to simply ignore the tree labels and then just evaluate based on tree topology. But when we did look at these labels that were predicted, we looked at the empirical frequency of how often they corresponded to certain linguistic labels. And we did see clear alignments, like it was learning certain non-terminal labels that corresponded to noun phrases. So it was definitely learning something meaningful, which
Yeah,
was
yeah.
nice to see.
I really liked another aspect of this, and maybe it was a more speculative quote, but so I'm reading directly from the
Mhm.
thesis here. It says it's possible that the model is utilizing subtrees to capture broad template-like structures and then
Yeah, yeah.
using Z to fill them in. And I thought that was a really nice intuition. So, did you get this intuition that this is occurring? And do you think that building in these types of ideas could be useful for generating text, for instance?
Yeah, so we did see some evidence for that happening where, for example, if you get subtrees that had the same subtree structure, the discrete structure, and then you cluster the sentences based on the Z, with say PCA, you get constituents. Well, you get things that model things are constituents that have the same syntactic structure. For example, they're prepositional phrases, but have different lexical realizations. So this hinted at something like disentangling of syntax and semantics. I hesitate to use the word syntax and semantics because I think the way sort of I use it or like NLP people in general use it doesn't give justice to the richness of syntax and semantics as a discipline. But at a hand wavy level, maybe it's disentangling syntax or semantics, or a better way like disentangling what to say from how to say it. It's interesting you mentioned the utility of this on
Hmm.
text generation. Yeah, it is something I'm thinking about. It turns out even with the compound extension, like the model is still nowhere near as powerful enough to generate coherent text. Like perplexity of these models are in say the high 100s, whereas if you just have a vanilla RNN language model, it's in the 70s to 80s depending on which version of PTB you use. Um,
Yeah, yeah.
but yeah, so it'd be interesting to see whether this will allow us, these models at scale will allow us to automatically generate and provide you sort of like switch into the internals of the generative process. So you can say, I have a sentence like this. I want to capture the content of this, but say it like another sentence. And another aspect is even just from the perspective of learning like representations. I think this line of direction could be interesting. Like, can we, for example, capture for a given sentence two representations? One captures how to say it, and another captures what to say. And there's very interesting work from various folks doing this. Some people at UWash, some people at TTIC. But this could be another technique for doing this as well, which is, I think, somewhat underexplored.
Yeah, then I was thinking if you had, say, a large document, for example,
Mhm.
then some large documents might have a certain structure. So if you could somehow disentangle that, uh, use this latent representation as sort of a planning mechanism for generating the document.
Yeah, right. That'd be definitely interesting. Although I hesitate to speculate whether the formalism of context-free grammars is the uh, right mathematical tool
Right, right,
for
right.
capturing like say sentence level discourse.
No, I was really zooming out and just focusing on
Oh, this notion of
the
like
template
yeah,
like
yeah,
notion. Yeah.
yeah.
Yeah, after doing all this work, so on continuous latent variables, discrete latent variables, trying to incorporate them into different types of models,
Mhm.
what's your outlook on continuing with these? Do you think you'll still keep studying these and trying to take them further, or do you see yourself maybe looking into other things?
So one area that I'm thinking about, which I haven't even started, is like revisiting some of the classical tree transduction grammars, like sort of like synchronous grammars for sequence to sequence learning. And I think it'd be interesting to revisit these classical formalisms, again with the tools that we saw with the neural PCFG work that made it work well, i.e., neural parameterizations and making things more flexible with, say, with richer generative models that make inference intractable, but that are trained with amortized variational inference. So I think I'm interested in revisiting these synchronous grammars for sequence to sequence learning, and this would be an empirical investigation where, like, hopefully, um, these models have a better inductive bias than classical seek-to-seek methods, so that, say, they are more data efficient. Now,
Mhm,
I don't think on like machine translation they'll be at all competitive with the current fully connected seek methods, but maybe on lower resource languages or on tasks where
mhm,
compositional generalization is more important, these types of uh, classical tree transducers will do better. So that's on the
mhm,
engineering empirical extensions of these hierarchical latent variable models. I think on the more scientific or cognitive science side, it'd be interesting to investigate different formalisms than context-free grammars that have been posited to govern human language structure. For example, like mildly context-sensitive grammars, such as tree adjoining grammars, have some very nice properties. And again, exploring how contemporary techniques for parameterization and inference can help learning of these models, and seeing how say the grammars or the structures that you get can be used to obtain metrics that correlate better with human electrophysiological activity, or seeing how these can, say, confirm or disconfirm the different theories of syntax that are hypothesized to govern human language. It's not a very good. Uh, it wouldn't be like sort of like the best evidence, but it would, whether if you have some formalism and you train it on raw text and you discover some tree structure, and whether that agrees or doesn't agree with um, phenomena that's hypothesized by linguists, I think provides one level of empirical evidence for or against different hypotheses uh, that are that are hypothesized to govern human language. So that would be
Hmm.
the more scientific extension of these hierarchical latent variable models. But both of these are very speculative. So
And then I'm guessing that probably in doing this investigation,
mhm.
it might be similar to your thesis, where this requires new learning or inference methods in
Yeah,
order to
maybe.
achieve these things.
Mhm.
Yeah, that is fascinating to hear, though. Kind of tracing it back, I mean, maybe you got interested in these RNNGs, and then those had this correspondence with neural activity, and then it sounds like maybe that played a part in your interest in exploring this further now.
Mhm. Yeah, I think definitely.
You'll be starting in July of 2021 as a assistant professor at MIT. So anyone who's listening, if this sounds interesting to you, I'm sure you'll be taking some students to study
Yeah,
these
I'll
types of
definitely
things.
be looking for some students. So if you're interested, please yeah, mention this on your mention my name on your application, and please feel free to send me an email.
This is always a hard question to summarize about advice, but do you maybe have advice to maybe someone who's starting a PhD and is interested in latent variable models, or it doesn't have to be specific to latent variables, just some general advice?
First of all, I think in general it's probably not. Uh, well, this itself is advice, but it's probably not a good idea to like rely on advice from people who have like survived. You know, there's the sample bias. Looking back, I can really say like I was just very lucky, both in terms of like some aspects of research turning out well, and both like sort of like getting into deep learning at the right time, meeting my advisor at the right time, and these are all just very serendipitous events that you can't plan for. Under this view, I think it's you can't plan to be lucky, right? I think in some sense you should do what you find interesting, and if it turns out you're lucky, that's great. Yeah, if I reflect back on my PhD, I was just incredibly lucky with a lot of different things, and um, and this certainly does inform uh, my thinking about like how many people aren't exposed to opportunities that don't even like have the opportunity to be lucky, and I think this does
Right,
inform
right.
like how I think about like say teaching computer science, about diversity and inclusion in tech, um, and just not to like go off on a tangent, for example, for like not to derail this conversation, like I, I I got into computer science like pretty late. So in undergrad, I studied math and econ, and I took one computer science class, which was required for math majors, and this was like Intro to CS, which was like a MATLAB based intro to programming course, and I hated that course, and it was one of my worst classes at during my undergrad. And looking back on it, I think the part of the reason was like clearly like 80-90% of the class like had exposure to programming before coming into this class, and me learning this from scratch, I felt like I was like very far behind, and I felt like there was no motivation to catch up because I thought I would never be able to catch up to them. um, and now like sort of in my early 20s, I was again serendipitously exposed to programming through my job, and that's how I picked it up. But so I got lucky, but then I think about like how many people get that similar experience in their first CS class, and this was coming from someone who's like as an Asian male, like part of the majority demographic, right? So if you think about that, that certainly informs, like for example, how I want to teach my classes. But these are sort of nascent thoughts, and I think I'll be thinking more harder about them as I think about drafting crafting courses and such.
I guess like having some underlying interest that's driving all of it, and like staying focused, but then um always realizing that so many steps along the way there is a factor of luck,
Yeah.
and yeah, so trying to open that up to as many people as possible.
Mhm.
And then I think a separate branch of it is it also I think it's also a commentary on science itself, that you could read a paper and look at the results and kind of see the mathematical derivation,
Mhm.
but like maybe to actually get it to work in practice, it was or some like lucky things that fell together, and so now this is what we now know about as a result.
Right, right.